Dr. B. Be sure to watch the Edpuzzle video on Hardy-Weinberg before you watch this. This is just more of a specific um, kind of video to show you exactly how you would use the Hardy-Weinberg in a scenario that you would potentially see on a test in, I guess, what, 2 weeks? All right, so the question they had, obviously, she was talking about birds, and some of their feet had webbing and some didn't. So let me just make up an example. So if there happen to be, I don't know, 1,000 birds, and if from that 1,000 birds there happen to be, let's just say, what's a good number? 900 that had webbing and 100 that didn't have webbing, we can use Hardy-Weinberg to figure out basically the relative allele frequency. So if you recall from lab this week, I gave you a whole bunch of cards that had big A and a little a, right? And so the idea of this is what's the frequency in the population of, and again, in our case, with the birds, it just happens to be a big N and a little n, so it doesn't matter really what the letter is. So we want to know the frequency of how much n's are in the population and how many little n's are in the population. And if you recall from the lab we did, if you happen to be this, you know, we knew what you were. If you happen to be this, we knew what you were. And if you happen to be this, we knew what you were. But in reality, and you should realize this, we would never know these guys. In other words, you can't look at somebody and just know their genotype, that they're big A, little a. So for example, like, you know, in the case of, you know, let's just say an earlobe, right? That's a normal earlobe. That would be, let's just say big A, or big A, little a. And then some people have earlobes that attach directly to their head. That's recessive. So you would know that one by looking at it, but you wouldn't know which of these two it is. So Hardy-Weinberg can help us figure out the frequency of these alleles in a population based on a sample size. So basically how this works, regardless of what the letter is, we always call the big one letter P, right? And then we call the little one Q. So in this case, P would refer to the big N and Q would refer to the little n. And if we refer to the lab we did last week, P would be the big A and Q would be the little a. It's just kind of what we use. So that would be the cards, if you can think about it, right? And all the cards, if I had you guys at the end of lab come up and put all of your cards into 2 piles, right? You'd be putting your big A's in this pile, and you'd be putting your little A's in this pile, right? That's basically kind of knowing that that's 100% of the population. So therefore, all the P's plus all the Q's equal 100% of the population. It's almost like saying in the case of the birds, or in the case of you guys, with last week it'd be all the big A's plus all the little A's equals 100% of the population. Or in the case of the birds, all the big N's plus all the little n's equals 100% of the population. We just happen to call P and Q a symbol for the larger and the smaller allele. So based on that, we can use this to kind of extrapolate and figure out the numbers of A's in the population, or numbers of N's and numbers of big N's and little n's, and also the heterozygotes. So here's how you would do it. Basically, if you look at this, we have birds that look like 3 different kinds of birds in terms of what they would be. Any bird that looks like this is going to be this, or is going to be this. We don't know the difference between them, but we do know that all the birds that look like that are that. Okay, so we already know something, okay, because we're here to figure out, and I'm going to go down to kind of the bottom here, that we basically want to know the population of all them plus these equals 100% of the population. In other words, they're either going to be homozygous dominant, heterozygous, or homozygous recessive, and that's going to be 100% of the population. So how do we go from here all the way to here? Basically what we do is we can figure out already one thing. We know that all of these 100 birds with no webbing are this. We know that already. So basically, in order to interpret this, we can expand this first. So watch this. We know that there's 2 letters, not 1. Notice that, by the way, all of us, because we're, there we go, diploid, have 2 letters. This only represents 1. So what we can do is we take the P plus Q and we square it. This goes back now to 7th grade math, actually. And we get the math of, if you remember FOIL, p squared plus pq plus pq will be 2pq plus q squared equals 1. Now, don't get freaked out. This math is not that difficult, all right? So really what that means is p squared is this, right, which is the big N. Q squared, which is the little letter, is this, little n, and 2pq, this whole value represents the heterozygous, right? So we already know one of these three. And the one that we know already right now is this guy. We know the little n population because basically, if we look up here, it's 100 out of 1,000, right? So we know that if we take 100 out of 1,000, we get, let me write the whole thing, whatever this is plus whatever this is plus 0.10 equals 1. This is 10%, right? It basically took 100 over, 1,000, and I know that 10% of them are that, okay? But what I don't know are the other ones. But here's what I can do. I can use this to figure out what the other two are, okay? So the way that I would do that is if I know that q squared is equal to 0.1, I can use my calculator to figure out q. Then I can know that p plus q is equal to 1. Then I can use that to solve for p. Then I can use that to solve for p squared. I know that sounds crazy. It's not that crazy. Let me go through it. So if I turn on my calculator here, and hopefully you can kind of see this, right? If I know that q squared is equal to 0.1, then I need to take the square root of 0.1, right? Which is going to be, because I want to basically square these. So, and I get 0.316. So therefore q is equal to 0.316. Okay, and to test it, does 0.316 times 0.316 equal somewhere really close to 0.1? It does, so that's right. See how I'm right on that? So now I can do this one right here, because now I know that p plus q is 1. So if q is 0.316, therefore 1 minus 0.316 is going to give me what p is. 1 minus 0.316 is going to give me, p is going to equal to 0.684. And if p is 0.684, then p squared is, let me go ahead and hit the squared button, 0.467. So now if I go back over to here, I know that this is 0.467. So basically 46.7% of the population is probably big N, big N. 10% of the population is little n, so therefore I really have to do now 2nd grade math and figure out, well, this plus this unknown plus this equals 1. So all I now have to do is just say, right, 1 minus 0.467 minus 0.1 is going to equal 2pq, which is basically this and this. So I'm going to take, right, clear, 1 minus 0.467 minus 0.1, and it's 0.433. 433. So to see if that works, does 0.433 plus 0.467 plus 0.1, notice gives me 100%. So now I know that this value, this is basically the answer, right? And the question was, what percent of the population of 900 webbed feet and 100 non-webbed feet, what is the allele frequency of the big N's and little n's? Well, based on that, 46.7% of the organism, of the birds have big N, big N. 43.3% of them have big N, little n, and 10% of them, the part that I knew from the question, have the feet that are not webbed. So this is an example of how to do Hardy-Weinberg, and the easiest thing obviously to do is follow this train. This is just basically a train that never changes, right? You know your q squared because that's always going to be the percent of this over the 100. So once you get that, it's find q, then find p plus q, then p, then p squared. So I'm going to throw a couple more examples online for you to help for the test. You'll have a question or two on Hardy-Weinberg on the test. Don't forget to check out the PowerPoint as well. And the questions that I pose for you are going to look literally exactly like the ones that I'm going to give you. I'm just going to have different numbers. So hopefully that helped, and let me know if you have any questions.